Hello and welcome to the Chapter 11 lecture, Part 1. This is a chapter all about solutions. So you may or may not recall that we were actually introduced to solutions in first semester in Chapter 6 of the textbook. So this is a little bit of review. There's some stuff that's a little bit redundant that you might find, but it's, I think, always helpful to have those reminders and refreshers. And then we're also going to learn some new things about solutions. So in this part, in part 1, we're going to be doing a lot of the math. We're going to be repeating, I'm going to be reminding you what solutions are, how they're made. I'm going to drop some little like Easter eggs. I don't know if that's the right term for it. Some little primers for some future information, a little bit more about thermodynamics that we're going to get into soon. And we're going to review some concentration calculations and also learn some new concentration calculations. So, starting with a little review, what are solutions? A solution, I need a pen. Solutions. A solution is a homogeneous mixture, meaning that everything is evenly dispersed throughout the mixture, and it can be two or more chemicals. We generally are going to be dealing with solutions of two things, one solute, one solvent, but technically solutions can have many solutes. So when chemicals mix together, and they diffuse into one another, they do this because of a thermodynamic principle called entropy. And entropy is defined as the tendency to spread out and become less ordered or more random. And we're going to learn more about entropy when we talk about thermodynamics, but we're just going to introduce it right now. So just an important point that solutions can take place in any state of matter. You can have solid solutions. So a lot of metals are alloys. They are blends of different metals. So bronze, for an example, is not an element you can find on the periodic table. It is a metal alloy. Same with steel. Liquid solutions are the ones we're probably most familiar with and have most of our day-to-day interactions with and think about as solutions. And then you can also have gas solutions. So air, the air we breathe is a mixture of carbon dioxide and oxygen and nitrogen and hydrogen. So it's really a solution. So the components of a solution, the two parts, are the solvent and the solute. The solvent is the more abundant of the two. It's the chemical that's in the greatest amount. And the solute is the thing that's in the lesser amount. So we usually say the solute is dissolved in the solvent. So what is actually going on in this dissolving process? So I'm going to change my pen color to black here. So when we have a solution being formed, so let's say we have our let's call this our solvent, and this our solute. All right, so in the solvent, let's call it water because that's a very common solvent. All right, you have these intermolecular forces, right? I'm going to put IMFs. And same thing within the solute. You have intermolecular forces that are holding all of these or attracting all of these molecules together. So in order to break, or I don't want to say break, in order to separate the particles, you have to overcome those intermolecular forces. And then you form new intermolecular forces between the solvent and solute molecules in the solution. All right, so in these we are disrupting the intermolecular forces. We need to I don't want to say break, but disturb those intermolecular forces, overcome those intermolecular forces in the solute and solvent so that we can establish new intermolecular forces between the two molecules when we make a solution. So solutions will form based on intermolecular forces or attractive forces. In order for them to mix, they have to be able to overcome the attractive forces within themselves and establish good, strong intermolecular forces with each other. And this is a cool table right here that I just want to call your attention to. So if the solvent-solute interactions, so these interactions here, if they are stronger than these interactions, then a solution will generally form. If the solvent-solute interactions are equal to the solvent, the interactions between the solvent and solute individually, usually a solution will form in that case too. But if the interactions between the two different substances are weaker than the interactions that each substance has within itself, okay, then a solution oftentimes will not form. Now, it can still form if there is enough entropy. So if the entropy is strong enough, the sort of pull to randomize, then it might still happen. But these are just some sort of general rules looking at those intermolecular forces. So some other terms that we should know when we're dealing with solutions. Every solute has a solubility, a defined solubility within a given solvent. So solubility is just a measure of how much solute can dissolve in a given amount of solvent. If something is soluble, if it dissolves in a solvent, we say it's soluble. Another term for that in chemistry is we say that it is miscible. So miscible and soluble are synonyms, and immiscible and insoluble are synonyms as well. So just alternate terminology there that you might see. So when it comes to solubility, something's going to actually be soluble in something else. It usually has to follow this golden rule. The golden rule of solubility is like dissolves like. And what do we mean by that? We mean that things with like intermolecular forces or like attractive forces will dissolve each other. So nonpolar things will dissolve other nonpolar things. Polar solvents will dissolve polar solutes. That's because nonpolar substances, the only attractive force they have are those London the London dispersion forces. I put L disperse. Sometimes they're called dispersion, sometimes they're called London forces. Either way, London dispersion forces are what hold our nonpolar substances together. It's the only attractive force they have. And polar substances have stronger attractive forces. They have dipole-dipole or hydrogen bonding that can attract them together. All right. Polar solvents can also dissolve a lot of ionic compounds, and that's due to the strong ion dipole forces that occur in solution when we mix the things together. So the reason that polar and nonpolar do not mix, all right, is again explained by this chart here. So if you have a like a polar substance and a nonpolar substance, all right, their attractions to themselves are going to be better than the attractions they have with each other. They'll be greater than the attractions they would have with each other. And so in a lot of cases, the solution there does not form. They are not soluble. They are insoluble or immiscible. So let's just do a little sample problem here, an example problem, sort of a context check. Vitamins, this is a true story. Vitamins are classified as either fat soluble or water soluble. Classify each of the following vitamins based on their structures. Now you may know whether they are fat soluble or water soluble from maybe a nutrition course or something that you took, but we're going to figure it out from the chemistry. So let's first take a look at vitamin C. All right, so vitamin C, let's see, there's a bunch of carbons. This is a fairly large and busy molecule for you guys. We in general chemistry, we usually just stick with, sort of simpler binary compounds, but we can see there's a lot of carbons, but there's also a lot of oxygens. There's some lone oxygen here, and then there's an OH group, an OH group, an OH group, another OH group. So we know that there's a lot of electron hogs. There's even a few highly polarized hydrogens that could do hydrogen bonding. So this molecule is very polar. Vitamin C is very polar. And what else is very polar? Water. So vitamin C is going to be water soluble. Very soluble in water. Fat, on the other hand, is not soluble in water. Fat is nonpolar. Water is polar, fat is nonpolar. So let's look at vitamin A over here. I do see an OH down here, which could do some hydrogen bonding, but all the way else through the molecule, all I see is carbons and hydrogens. All of this screams nonpolar to me. So vitamin A, we would say, is mostly nonpolar, and so we would classify it as fat soluble, unlikely to be water soluble, and that is in fact how each of these vitamins are classified. And you'll find vitamin A in a lot of things that have fat in it, like whole milk. You'll also find a derivative form of vitamin A in some vegetables, like carrots. Beta carotene can be converted by the body into vitamin A. But those things are not fatty, so it's not a great example there. I digress. All right, another concept check is we're going to look at this table here, and we're going to explain the trend of solubility in the following alcohols. So as we go down this table, we're just adding a longer and longer chain of carbons and hydrogen. So we start with methanol, which has one carbon and then an OH group, and then ethanol, which has two carbons and then an OH group, and so on and so forth. So this carbon chain just gets longer and longer. So these small alcohols, methanol and ethanol, have very good solubility in water, infinite solubility in water. And even propanol, all right, has infinite solubility in water. But as we go down the table, we find that there's less, and that these alcohols become less and less soluble in water because their nonpolar regions get bigger and bigger. And as those nonpolar carbon-hydrogen regions get larger and larger, they become more soluble in hexane, which is just carbon and hydrogen and is very nonpolar. This is called hexane. Hexane is a classic nonpolar solvent. Okay, so you'll see this sort of opposite trend here. The more soluble it is in water, the less soluble it is in hexane, and vice versa. These solubility numbers, by the way, are reported in mole. This is 0.11 moles of that alcohol are soluble in 100 grams of water. Alrighty, so the process of forming a solution is known as solvation. We talked about state changes like vaporization and stuff. So this is just the name of this physical change. Solvation is a physical process. All right, so you have solute, which is just a bunch of molecules of the same material that are held together by intermolecular forces. All right, and those intermolecular forces are disrupted and the solute moves out and disperses within the solvent. All right, that's the force of, that's entropy taking action there, this diffusion reaction. So that's a physical thing. The chemicals are not changing. Notice you still have little blue balls and little orange balls. We haven't changed the chemicals at all. We've just evenly mixed them together. So that is a physical process. So another term for solvation, if we're solvating a solute in water, we call it hydration. So hydration is dissolving a solute in water. So if we look at the energetics of this dissolving process, this solvation process, we can measure the energy changes, and energy changes are measured as the heat of a reaction or the enthalpy of a reaction. And there's sort of three energetic steps that have to occur when we form a solution. So the first thing is we need to separate the solute particles. So we have some solute, they're held together by intermolecular forces, right? These things are attracted to each other by London forces or hydrogen bonds or whatever it is, depending on the solute. So the first thing we need to do is we need to add energy in order to separate those. Disrupt those intermolecular forces. So I sort of diagrammed that here too. So that requires an input of energy. So the heat of this step, we'll call it step 1, is positive. It's endothermic. It's going to absorb energy. All right, we also need to do the same thing with the solvent. It also is going to absorb energy. We'll call this step 2. And it is also endothermic, right? We require the input of energy, move these particles faster, and separate them, get rid of those intermolecular forces between them. And then in step 3, when we combine them, we are going to re-establish intermolecular forces, but now they will be a lot of times through the different particles. And when we reestablish intermolecular forces, that is exothermic, has a negative delta H. All right, so we can calculate the heat of this physical process. So we talked about the heat of vaporization in the last chapter. So the heat of solution or solvation is going to be the enthalpy of each of these 3 steps added together. All right, so the heat of solution, the enthalpy of forming a solution, it can be endothermic or it can be exothermic. Remember, these 2 steps are endothermic, this step is exothermic. So if these are not terribly endothermic and those numbers are small and this number is large, then you can have an exothermic heat of solution. If these numbers are large and this 3rd step has a small enthalpy, then the reaction will be exothermic. Right? In general, exothermic reactions in chemistry are more favorable. And we'll really get into that when we talk about thermodynamics. But exothermic reactions are more favorable. They tend to happen more spontaneously. So it's more common to have these exothermic solutions than endothermic solutions. But endothermic solutions will still occur if there is a favorable increase in entropy, in randomness. Again, molecules don't have thoughts and feelings and desires, but I like to think of them as having them, and they want to be have their space. They want to have their personal space. They prefer to be random. They prefer to be in a randomized state, and that is more energetically favorable, is what we say in chemistry. So entropy, the more entropy that a system has, the more stable it is. So even if something is endothermic, which is a less favorable condition, all right, if it's super random that way, then the reaction will usually still go. So solutions reach a type of equilibrium, and when they become saturated. So the different sort of levels of concentration of a solution are, you can have an unsaturated solution, you can have a saturated solution, or you can have actually even get a supersaturated solution. I feel like it sounds like a made up term, but it's for real, supersaturated solution. So an unsaturated solution is any solution that has less than the maximum amount of solute dissolved in it. So, anywhere from a pinch to a pound, as long as it fully dissolves, it's still considered an unsaturated solution. So an unsaturated solution still has room to dissolve more solute. A saturated solution is one where the maximum amount of solute is dissolved and no more can go into solution. And sometimes in a saturated solution, you have some solute that's undissolved still sitting at the bottom. All right. And so in a saturated solution, that's where we are at equilibrium. We're at a dynamic equilibrium. And it's good to always kind of think of equilibrium as dynamic. Dynamic means it's moving, it's changing, it's not staying the same. And so equilibrium is a state that looks like everything is staying the same. All right, but it's not really. There's actually constant movement. What's staying the same are the rates. The rate of dissolving equals the rate of precipitation. When you have a saturated solution, what's happening is it's not that no more solute can dissolve. It's that the solute is dissolving and crystallizing at the same rate. So the same number of ions or molecules are going into solution as they are recrystallizing. In an unsaturated solution, all of the molecules solvate. They all go into solution. None of them crystallize. But in a saturated solution, some of them start to crystallize and they ultimately reach a point where they're dissolving and crystallizing at the same rate. And that is what's happening in a saturated solution. Now, a supersaturated solution is kind of fun. So you can make a supersaturated solution usually by heating the solvent. So I'll show you down here. Solubility does depend on temperature. All right. For liquids and solid solutes like sugar and salt, all right, solubility as a rule generally increases as we increase the temperature. So as you can see in this chart here, here's temperature on the x-axis and here's solubility on the y-axis is measured, how many grams of solute per 100 grams of water. So it's just a measure of solubility. And you can see this is called a solubility curve. And it curves. I'll call this a solubility curve. And you find these experimentally. So you could do this for sugar and water. And you could find that at some, it's whatever temperature here, you can dissolve this many grams of water, of sugar in water, but as you raise the temperature, you can dissolve more and more grams of sugar in water, right? And we know that from life. If you've ever had hot beverages or cold beverages that you needed to sweeten, if you're a tea drinker, all right, sugar dissolves much better in hot tea than it does in iced tea. So that kind of is our everyday go-to example. So as we increase the temperature, we increase the solubility. So this line represents the point of saturation. That's the maximum amount of solute that you can dissolve in a solvent at whatever given temperature, right? But if you raise it to, if it's, when it's warm, so you could add, let's say, this much, let's call that 50 grams of sugar to warm water, all right? And then you could cool the water off. And usually when you cool the water off, so you bring the temperature down here, okay, so now we've cooled the water off and now we're at this point, okay? What usually happens is the sugar will start to crystallize and fall out of solution. But sometimes if you cool it really gently, the sugar will stay in solution. And so you'll actually have a solution that's super saturated. It has more sugar dissolved in it than should be dissolved at that temperature. But super saturated solutions are really fragile. They're really sensitive. And if you just touch them or you add a little crystal of sugar or you shake the tube a little, you will start that, you'll basically trigger that crystallization process and it'll all crystallize kind of right away. So this is actually how rock candy is made, how candies are made. You melt a bunch of sugar, you heat up water or oil or something. I actually can't even remember now. And you melt sugar into it, so you dissolve a lot of sugar, a high amount of sugar, and then as you bring the temperature down, it crystallizes. It cools. As it cools, it crystallizes, and so that's how you make candy, is through super saturated solution of sugar. Let's see some other things. Gases. Gases are also soluble in liquids. All right, but for gases, when we increase the temperature, it usually decreases the solubility. So it has the opposite effect. Temperature has the opposite effect on gases. And here's a solubility curve or solubility curves for several gases. And you can see that as we increase the temperature, we are decreasing the solubility. And here's oxygen, which is a good example. So I guess I should have an example here, like a real life example like we had with the tea previously, the hot tea versus the iced tea. All right, the real life example here is, think of carbonated soda or carbonated beverages. All right, when they are cold, they stay carbonated better. And when they are warm, they go flat. In other words, they lose the carbonation. They lose the carbonated, by the way, just means they have dissolved carbon dioxide in them. So the solubility of carbon dioxide goes down as temperature goes up. So CO2 goes down as the temperature goes up. And that's why you want to keep your soda cold and not warm, unless you don't like the carbonation, and then warm it up as much as you want. So another thing for gases specifically, again, we're just talking about gases here, the solubility of gas also depends on pressure. So pressure pushing down on a gas essentially pushes it into the liquid. And this is, again, thinking of carbonated beverages, how they are made. So they are made by basically injecting pressurized carbon dioxide into them. And the carbon dioxide dissolves in the water. And then that high pressure, then you seal the can or the bottle and you keep that carbon dioxide in there. But once you open the bottle, even if you keep it cold, it'll still go flat, because that pressure, you're removing the pressure of gas on top of it. And so the carbon dioxide will slowly leave the bottle. So there is a mathematical equation that allows us to determine what the solubility of a gas is in a solvent. This is solubility. And this is called Henry's law. And Henry's law is Henry's constant times the pressure of the gas. And that will tell us what the solubility of the gas is. So there's a Henry's constant for each gas. So for example, if you wanted to figure out What's the solubility of carbon dioxide in, I don't know, Diet Coke? All right, we could look up what is the Henry's constant for carbon dioxide, and we'd have to know what is the pressure of carbon dioxide in this pressurized can or bottle, and then we could calculate what the solubility of carbon dioxide is. And the Henry's constant, I think, is also specific for certain temperature, based on temperature. So you can do mathematical problems here. We are not. We are going to choose to spend our math energies on concentrations. So there's a lot of math here to do. So when it comes to concentration, remember, a concentration is just the amount of solute in a solution. It's a way to express the amount of solute in a solution. And there are many ways that we can do that, because we can measure moles of solute or mass of solute or percent of solute. So there's 4 different ways that we are going to learn or review on how to indicate or measure concentration. The first one that's used the most in chemistry is molarity. And molarity is abbreviated with a capital M. And molarity is the moles of solute per liter of solution. All right, and these details are important. Moles of solute, not moles of solvent, not moles of solution, but moles of solute per liter of solution. The units, therefore, of molarity are moles per liter, but we often just abbreviate it as molar with that capital M. So let's do a practice problem. A solution is prepared by dissolving 16 grams of potassium chloride in enough water to make 250 milliliters of a solution. Determine the molarity. So the way I like to start these problems, I like to write out any formulas I might need to use. And molarity, I know that molarity is moles of solute per liter of solution. So do I know the moles of solute? I don't see moles given to me anywhere. Do I know the liters of solution? Well, I have 250 milliliters of solution. I can convert that to liters. I can do that in my head. So the liters of solution are 0.250 liters. 250 milliliters is 0.250 liters. But now I need moles of solution. And I could figure that out because I'm given grams and I'm given a formula. So I'm going to just kind of do that to the side here. If I have 16 grams of KCl and the molar mass of KCl I can calculate by adding the molar mass of potassium and chlorine, and that's going to be a molar mass of 74.55 grams. All right, then I get moles, and when I do the division here, I get 0.215 moles. So now I can just plug that in here, 0.215 moles of solute per 0.25 liters of solution equals, type it into my calculator, 0.860 molar. That's the molarity, the concentration of this solution. So that's molarity. Now, another way to calculate or quantify concentration is an almost same sounding term, not molarity, but molality. Molality is abbreviated with a little italic lowercase m, and it is also having to do with moles of solute, but this time it's over kilograms of solvent. Remember, these little details are important. So the units would be moles per kilogram, or we just write molal. So this up here was an 8.86 molar solution, and we're going to solve in this problem, figure out what the molality is. So in this one it says if you combine 25 grams of a solute with a molar mass of 50 grams per mole with 150 grams of solvent, what is the molality of the solution? Sometimes it may be helpful for you to draw pictures. I like to do that sometimes. So if I just say like, oh, here's my solute, and it says I have 25 grams, and then it says I'm combining that with solvent, 150 grams, and it wants to know what is the molality of the solution. So I'm trying to find molality. And I know that molality is moles of solute over kilograms of solvent. So I need to find these things. So do I have moles of solute? No, it did not give me moles of solute, but it gave me the mass of the solute and the molar mass of the solute. And I can always find moles from the mass. So let's do that first so I can figure out the moles of solute. I'll just color code this in green, okay? So moles is represented by an N, letter N, but can represent moles, like in Pivnert, our ideal gas law. All right, so the moles will be the mass of our solute times, or divided by the molar mass. 1 mole is 50.0 grams. So that means we have 0.50 moles of solute. So I'm going to plug that in up here in my equation for molality. And now I need to know how many kilograms of solvent I have. Well, it tells me I have how many grams of solvent I have. So I just divide that by 1,000 to turn it into kilograms. So 0.150 kilograms. And now I do the math. 0.5 divided by 0.150 is 3.33 moles per kilogram, or 3.33 molal solution. All right, so that's 2 ways. Now for a third way that we can measure solution, molarity, and this third way, percent mass, should be things you remember from chapter 6. These are review. Molality is new. We haven't talked about molality before. But percent mass of a solution is equal to the mass of the solute divided by the mass of the solution, and then to make it a percent, multiply it by 100%. Okay, so the unit here is just percentage. The mass units don't matter as long as they are the same. So it could be grams of solute over grams of solution, or kilograms of solute over kilograms of solution, or pounds. It doesn't matter what the unit is as long as the unit for both is the same, because it's a percentage. So the unit, the mass units just need to cancel out. They just need to be the same, so they cancel out. All right. Oops, I forgot to subscript these. Sorry. That's supposed to be C12H22O11, which is the molecular formula for sucrose. What mass of sucrose in grams is in 355 milliliters of a soda that is 11.5% sucrose by mass? And it gives us a density. So it gives us a lot of stuff here. So sometimes it's just helpful to start writing out the stuff you have before you necessarily figure out how it is you want to do the problem. So I'm just going to start writing out stuff. So I have a volume, that's 355 milliliters, and that's of the solution. And I have a percent mass, and the percent is 11.5%. And that is talking about the sucrose, the solute. And then I also have a density of 1.04 grams per milliliter. And this is a density of the soda. The soda is the solution. So I'm just like noting what I'm given, you know, whether the mass or the volume or whatever is that of the solution, of the solvent, or of the solute. Okay, so I have these things. Now I'm going to write out some formulas I might need. So I can write out the formula for percent mass. What does that percent mean? It means that the mass of solute divided by the mass of solution times 100% is 11.5% in this case. And I'm given a density. And what is density? Density is mass over volume. Okay, so now I kind of like to check off what are the things I have and what am I trying to find. Oh, I should write first what I'm trying to find. What is it asking me for? What mass of sucrose? So I want to know the mass of sucrose, and sucrose in this case is our solute. So I just put my little question mark there. That's what I'm trying to find. All right, so that thing I'm trying to find, I'll put that in green, all right? That's this. This is my X, the mass of solute up here. So I know the percent mass. I'm given that right here in the equation. And so in order to solve for the mass of the solute, I need the mass of the solution. I need the mass of the solution, but I'm not given the mass of the solution. But I'm given volume and I'm given density. Could I use those to figure out the mass of the solution? Yes, I can, because I can use the density equation. If I know the density and I know the volume, I can solve for the mass of the solution. And then I can plug that in down here, and then I'll be able to solve for the mass of the solute. Okay, so that's exactly what I'm going to do. I'm going to start with the density formula, and I'm going to solve for the mass of the solution. So I'm just rearranging that equation. So the mass of the solution is equal to density times volume. And the density is 1.04 grams per milliliter. And the volume is 355 milliliters. My units of milliliters match and therefore cancel out. And so the mass of the solution is 369.2 grams. So that is my mass of solution. Now I know the mass of the solution. I might even write it down over here. Mass of the solution is 369.2 grams. So now I can use this equation and solve for X. So I know the percent mass is 11.5% equals X. I'm trying to solve for the mass of the solute over 369.2 grams times 100%. So I'm going to divide, I'll multiply both sides by 369.2. And I'll divide both sides by 100%. So this will cancel, and this will cancel, and then I'll be able to solve for X. X is 369.2 times 11.5 divided by 100. So X, our mass of solute, is 42.5 grams, 3 sig figs, because I'm given 3 sig figs. And I'll even say 42.5 grams of sucrose is how many grams of sucrose are in a 355 milliliter can or bottle of soda that is 11.5% sucrose by mass. And then the fourth method of quantifying concentration is with a mole fraction. A mole fraction. And the symbol for mole fraction is the Greek letter chi, which just looks like a capital X, maybe in italics. All right, so the mole fraction it's just a proportion. It's the moles of solute per moles of the solution. So another way to write that using N for moles. So the moles of solute over the total moles. So that would be the moles of solute plus the moles of solvent. Remember, solution is solute plus solvent. All right, there's no units for mole fraction. There's no units. It's just a proportion. A fraction, a percent, kind of, except written as a decimal. It always comes out as a decimal. So in other words, if you have the mole fraction of the solute, all right, and the mole fraction of the solvent, they are just the two proportions of the whole. They should add together to equal 1. So all the mole fractions of all the solutes in the solvent should add up to 1. It's just a proportionality. So let's do a practice problem for this. You prepare a solution by dissolving 17.2 grams of ethylene glycol, so this is our solute, in 500 grams of water. The final volume is 515 milliliters, so that would be the volume of our solution. And now it wants us to calculate the following. So it wants us to use this information to calculate the concentration in all 4 different ways. And we can do that. So let's start with A here. All right, so for A, molarity is moles of solute, and I always start by writing out the equation for that type of concentration to make sure I'm plugging in the right things. And I encourage you to do this in your homework, but especially on your tests. All right, so do I know the moles of solute? The solute is the ethylene glycol. I don't know the moles, I just know the mass, but I can always convert mass to moles using the molar mass. That's stoichiometry 101. So 17.2 grams of ethylene glycol times the molar mass of, or divided by the molar mass of ethylene glycol. So the mass of 2 carbons plus 6 hydrogens plus 3 oxygens is equal to 62.1 grams. So that comes out to 0.277 moles of ethylene glycol. So now I can plug that into my numerator down here, 0.277 moles. And then I want to know over liters of solution. I look in my problem and the volume I have is 515 milliliters, but I need my units to be in liters specifically, so I'm going to convert that. I just do it in my head. I divide by 1,000 because I know there's 1,000 milliliters in a liter. And the molarity is 0.277 divided by 0.515, which comes out to be 0.538 moles per liter. Per liter, or 0.538 molar. So this is the molarity. Now for part B, the molality is that lower italic letter M, and it also deals with moles of solute, but this time it's over kilograms of solvent, not solution, but solvent. So I know the moles of solute. I just calculated that already. 2.277 moles. Kilograms of solvent. The solvent here is the water, right? And I am given a mass of water, 500 grams. So to convert that to kilograms, that's 0.500 kilograms. So my molality is 0.554 molal. So they are similar, but they are not the same, the molarity and the molality. Now for percent mass, part C here. Percent mass is going to be my grams of solute divided by my grams of solution times 100%. So, and I look at the problem, I'm given 17.2 grams of my solute. All right, my solution, remember, the solution is solute plus solvent. I'm not given the grams of solution in this problem, but I am given the grams of solute and the grams of solvent. So on the bottom here, I'm going to do the sum of those two. 500 plus 17.2 is 517.2 grams. That is the mass of my solution, the mass of adding both of those masses together. All right, times 100% equals 3.33%. And then lastly, I can calculate the mole fraction. If I want to calculate the mole fraction of the solute, I need to know the moles of solute and the total moles. I'm going to put moles total, or moles solution would be another way you could write it. Okay, so I know that my moles of solute, I already calculated that up here, or right here, so that's 0.277 moles. All right, but I don't know the total moles, but I can figure it out because I know the mass and identity of the solvent. The solvent is water. I have 500 grams of water divided by the molar mass of water, which is 18.02 grams. And that comes out to 27.7 moles of water. And if I add these two together, I get the total moles is exactly 28.0 moles of solution. So that's the number I'm going to use in my denominator down here. That's the total number of moles. So the proportion of solute in this solution is really very small. It comes out to 0.00989. So that's the proportion of the mass of the solution that is sucrose, or ethylene glycol, sorry. We're on the ethylene glycol problem. So these are the four different expressions of concentration of this one solution. If we measure the molarity, the molality, the percent by mass, or the mole fraction. So practicing these problems till you get good at them is going to be key for this unit. All right, and then the last sort of highest level of math problem in this chapter is converting between units. So in the problems we saw before, we were usually given the masses of things and then we had to solve for concentration. But in this problem, we're given the molarity and we are asked we're given the percent concentration and we want to know what is the molarity. All right, so we're trying to find what is the molarity. And I just like I like to note somewhere, like, what is it I'm trying to find? Like, that's the first thing I need to make a mental note of. And then I'm just kind of trying to figure out, how do I get there? So a good way to start organizing your problem solving is to write out equations. So the equation for molarity is moles of solute per liter of solution. And I'm given the percent mass, so I'm going to write that equation out too. Percent mass is the mass of the solute over the mass of the solution times 100%. And I'm also given a density, so I'm going to write out the equation for density. Density is mass over volume. So now I'm going to kind of list out, well, what do I have? What am I given? So I'm given a percentage. The percent concentration is 0.656%. And what else? I'm also given a density of 1.03 grams per milliliter. I'm given a formula, so I also can figure out the molar mass of glucose, and it's 180.24 grams per mole. So that's what I have. So let me get my green pen out and start marking off. So I have this percentage here, and I have this density here, and that's it. It doesn't feel like enough information to find anything. Well, if I have a solution, okay, let's say I'm going to draw a picture of this problem here. That's weird. I just drew that arrow automatically. All right, so I have this flask, all right, of solution. All right, the concentration of this solution is the same in the flask of this volume as it is in a flask of this volume. All right, no matter what the volume of solution that I have, the concentration is still the same. So if I have 1 milliliter of it or 100 milliliters of it, the concentration is the same. So we can pick a volume here that we can pretend like we're working with. So I like to pick 100 milliliters because that's convenient. So I'm going to add that to my list. So now I have volume. I'm picking a volume of 100 milliliters. You can pick whatever number you want. And so if that's the case, then I have a volume. I can figure out now, I have enough information to solve for mass, for the mass of the solution. We're talking about the density of solution, the volume of solution. So I now have the information. I can solve for the mass of the solution. I can do that. And if I do that, then I will have the mass of solution here, and I'll be able to solve for the mass of the solute. That's cool. Okay, that's something. If I have the mass of the solute, well, I don't need the mass of the solute. I need the moles of the solute. But I can always go from mass to moles of anything by using the molar mass. So once I have the mass of the solute, I know I'm going to be able to get the moles of the solute. And then I'm going to need the liters of solution. Well, again, I just said the volume was 100 milliliters, so my volume, I know, is 0.1 liters. So I have that because I was able to arbitrarily pick a volume. So you can do that, and oftentimes need to do that to solve concentration problems where you're converting, and you can only do that really when you're converting between concentration units. because it doesn't, and the reason we can do that is because it doesn't matter what the volume is, that's not going to change the concentration of the solution. Okay, so now I'm going to work this in steps. So the first step I said I was going to do, the first thing I was going to do was I was going to use the density equation and find the mass of the solution. So I'm just going to rearrange that. Mass equals density times volume. The density is 1.03 grams per milliliter times the volume of, that we said 100 milliliters. So our milliliters cancel out, and we get that the mass of solution is 103 grams. All right, I'm going to put that down here, add it to my list. 103 grams. All right, then the second thing I said I was going to do was I was going to take that mass of solution and plug it into this equation next, the percent mass equation. So my percent mass that it gave me was 6.56% equals the mass of the solute, that's my x, that's what I'm trying to solve for, divided by the mass of solution that I just calculated, 103 grams, times 100%. I solve for x by dividing both sides by 100 and multiplying both sides by 103, which I don't have a ton of room here, so I'm just not going to do. But you do the algebra to solve for x, and you get 0.0. Nope, sorry, looking at the wrong thing. You get 6.76 grams. Now that's 6.76 grams of our solute. So I'm going to just add that to my list here. 6.76 grams of solute. Now I want to know how many moles of solute that is. So I'm going to use the molar mass. So this is sort of step 3 here now that I'm doing. So I'm going to take that mass and I'm going to divide it by the molar mass, which we said is 180.24 grams. My grams cancel out, and I get 0.0375 moles of glucose. And now I want to know what the molarity is. Remember, always remember what your end goal is and make sure you get there. So the molarity, now I have the information I need to plug into the molarity equation. Molarity is moles of solute per liter of solution, and I have 0.0375 moles of solute, and our arbitrarily decided 0.100 liters of solution comes out to a molarity of 0.375. So this 6.56%, so this solution, we could describe it as being a 6.56% by mass solution, or we could say it's 0.375 molar. Maybe try this one yourselves. Well, hopefully for a lot of these you try them by yourself and then you check yourself. But for this one, go ahead and try it by yourself, pause the video, and then see if you are correct. All right, I'm going to read the problem. Determine the molality. Molality is what I'm trying to find. If you have 65 grams of iron chloride, so okay, I've got start listing things out. I've got 65 grams of iron chloride, iron 3 chloride, and it's dissolved in 650 grams of water. And I want to know, and I also want to know what is the percent by mass. All right, so it's asking me for 2 things. So first, I'm going to write out the equation for molality. Molality is moles of solute over kilograms of solvent. And percent by mass, is grams of solute. Well, it's mass of solute, but I'm just writing grams over grams of solution times 100%. Alrighty, so what do I have? Now I'm going to start checking things off. So I do have the grams of solute. That is the iron 3 chloride. I do have the grams of solution, though not directly. The grams of solution, because this is the water is the solvent, so the grams of solution is going to be the sum of these two things. So 650 plus 65 is 715 grams. So that's the mass of my solution. So I do have that. So I can go ahead and figure out the percent mass right away. So percent mass is going to be 65 grams, that's my mass of solute, over 715 grams times 100%. So this is a 9.10% solution. Cool beans. Now for molality. For molality, I need moles of solute. Do I know the moles of solute? I do not, but I can figure out the moles of solute using the molar mass of iron chloride. So I'll just do that right over here. If I have 65.0 grams of iron 3 chloride, how many moles do I have? I need to divide by the molar mass. The molar mass is 218.05 grams. My grams cancel out, and I get 0.298 moles of iron chloride. So now I have moles of solute, check. And do I have the kilograms of solvent? I do. The solvent is the water. So the 650 grams of water, I just need to convert that into kilograms. So to solve for molality, right here, my moles of solute are, I calculated that to be 0.298 moles. And my kilograms of solvent is 650 divided by 1,000, 0.650 kilograms. So my molality is 0.459 mole, little italic m. So practice some of these in the homework. Get real good at doing, I call it sort of concentration math acrobatics. And then we will talk about colligative properties, or properties that solutions have that are different than pure solvent.